In the deepest reaches of the cosmos, there are objects that fire colossal jets of energy across billions of light years, and some of them are aimed directly at Earth. Imagine staring down the barrel of a particle accelerator the size of a galaxy. These are blazars, the incandescent hearts of distant galaxies, powered by monstrous black holes in a state of violent upheaval. They are among the most powerful and enigmatic objects in the known universe. Today, we're going to explore how we use one of our most powerful tools, radio astronomy, to peer into the hearts of these cosmic titans and unravel the secrets they hold about black holes, extreme physics, and the origin of the most energetic particles in the cosmos. At the center of most large galaxies, including our own Milky Way, lurks a supermassive black hole, a gravitational titan millions to billions of times more massive than our Sun. While many are dormant, some are active, voraciously feeding on a swirling disk of gas, dust, and shredded stars that have fallen into their grasp. This chaotic feeding frenzy creates what's known as an active galactic nucleus, or AGN, a compact region so intensely brilliant it can outshine all the billions of stars in its host galaxy combined. Some of the most spectacular AGNs launch colossal jets of ionized matter, or plasma, from their poles. Propelled by complex magnetic fields and the immense energy released near the black hole, these jets travel at speeds approaching that of light. Now, here's the crucial point. A blazar is a special and rare type of AGN. It is defined not by a fundamental physical difference, but simply by a matter of perspective. A blazar is an AGN whose relativistic jet is pointed almost directly towards Earth. This unique orientation has profound consequences for what we observe. Due to an effect called relativistic beaming, the radiation from the jet is dramatically amplified and focused in our direction. It's the cosmic equivalent of looking directly into a powerful searchlight, making the blazar appear extraordinarily bright and energetic. This alignment explains the defining characteristics of blazars. First, their extreme luminosity. They are among the most luminous persistent sources of radiation we can see. Second, their rapid variability. A blazar's brightness can fluctuate dramatically over very short timescales, sometimes changing significantly in a matter of hours, which tells us the emission is coming from an incredibly compact region. Third, they emit across the entire electromagnetic spectrum, from low-energy radio waves to the highest-energy gamma rays. And finally, they exhibit an amazing optical illusion known as apparent superluminal motion. Because the material in the jet is moving towards us at almost the speed of light, blobs of plasma within the jet can appear to be moving faster than light. This doesn't violate Einstein's cosmic speed limit, but is a geometric effect caused by the material nearly keeping pace with the light it emits. Astronomers classify blazars into two main categories: flat-spectrum radio quasars, or FSRQs, which show strong evidence of a dense, bright accretion disk, and BL Lacertae objects, which have weak or absent emission lines, suggesting they are powered by less efficient, starved accretion flows. To truly understand these objects, we need to see them in a light our eyes can't perceive. Our eyes are marvelous, but they are sensitive to only a tiny sliver of the full electromagnetic spectrum. Radio astronomy opens up a vast, invisible window on the universe, allowing us to detect radio waves, which have the longest wavelengths and lowest energies. Unlike optical telescopes, radio telescopes use large antennas, often shaped like giant dishes, to capture these faint cosmic signals. While stars dominate the optical sky, the radio universe is filled with things like the cold gas between stars, supernova remnants, and, most importantly for our story, the powerful jets launched by supermassive black holes. One of the greatest challenges in astronomy is achieving high resolution, the ability to distinguish fine details. For any telescope, resolution is limited by the wavelength of the light being observed and the diameter of the telescope. Since radio waves have very long wavelengths, a single radio dish would need to be impractically enormous, many kilometers wide, to achieve the sharpness of even a modest optical telescope. To overcome this, radio astronomers developed a revolutionary technique called interferometry. This method combines the signals from multiple, widely separated radio telescopes to function as a single, much larger virtual telescope. The resolution is determined not by the size of the individual antennas, but by the maximum distance or baseline between them. The pinnacle of this technique is very long baseline interferometry, or VLBI. VLBI networks link radio telescopes across continents and even in space to create an Earth-sized virtual observatory. This incredible feat requires meticulously synchronizing the data from each telescope using ultra-precise atomic clocks. All this data is then shipped to a central supercomputer, a correlator, which combines it to create images of unprecedented sharpness. It is this ability to achieve extraordinarily high angular resolution that makes VLBI the indispensable tool for peering into the hearts of blazars. The combination of Blazar's unique orientation and radio astronomy's high-resolution capabilities creates a perfect scientific synergy. While a blazar's jet is pointed at us, it's not perfectly aligned. This slight offset allows VLBI to resolve the structure of the jet, providing a side-on view of the plasma beam as it erupts. Through decades of radio observations, we have been able to map the anatomy of a blazar's jet. We see a core, the brightest, most compact feature at the base, and from this core, we can trace the jet outwards, observing knots and hotspots of emission that represent shock waves propagating through the plasma. These radio observations provide critical data on several key questions. First, jet collimation. How do these jets remain so tightly focused over thousands of light years? Radio images reveal the jet's shape, helping to test models that suggest magnetic fields act as a nozzle, confining the plasma. Second, particle acceleration. The radio emission itself is called synchrotron emission, produced when relativistic electrons spiral around magnetic field lines. By studying its intensity and polarization, astronomers can infer the strength and structure of the magnetic fields and learn about the mechanisms that accelerate particles to nearly the speed of light. And third, jet kinematics. By taking a series of VLBI images over months and years, astronomers can create movies of the jet's evolution. It was this method that first confirmed superluminal motion, providing direct evidence of the jet's relativistic speeds. The unwavering radio gaze on blazars has led to some of the most profound discoveries in astrophysics. The most ambitious VLBI project to date is the Event Horizon Telescope, or EHT. While its most famous achievement was capturing the first-ever image of a black hole's shadow in the galaxy M87, blazars are also prime targets. In 2020, the EHT collaboration released an unprecedentedly sharp image of the quasar 3C279, a well-known blazar. These observations peered closer to the central engine than ever before, revealing unexpected features at the base of the jet, including a twisted or perpendicular structure. This hints that the jet's shape is forged by complex, powerful forces very close to the black hole itself. More recently, observations of the Blazar J1924 to 2914 revealed a jet with a twisted, corkscrew-like magnetic field structure, which could be evidence of a binary supermassive black hole system at its heart. It is widely believed that magnetic fields are the key to launching and shaping these colossal jets. One theory, the Blanford-Znajek process, suggests that a spinning black hole can twist magnetic field lines, flinging plasma outward and extracting the black hole's own rotational energy to power the jet. An alternative, the Blanford-Payne mechanism, proposes that the jet is launched from the accretion disk itself, acting like a centrifuge. Radio astronomy, through measurements of radio wave polarization, provides a direct probe of these magnetic fields. Observations have revealed evidence for helical magnetic fields wrapped around blazar jets, a key prediction of these models. In fact, it seems the most powerful blazar jets require the immense power that can only be tapped from a rapidly spinning black hole in a special state known as a magnetically arrested disk, where the magnetic field is so strong it actually throttles the flow of gas onto the black hole. Another piece of the puzzle is what triggers this activity in the first place. Evidence from the Hubble Space Telescope, combined with radio observations, has shown a strong link between powerful radio jets and galaxies that are either currently merging or have recently merged with another galaxy. The Titanic collision provides a fresh supply of gas to the central black hole, triggering its active phase and the launching of the jets. For centuries, astronomy was a science of light. Today, we live in the era of multi-messenger astronomy, where we can combine information from electromagnetic radiation with other cosmic messengers, namely high-energy neutrinos. Blazar jets are not only powerful light sources, but are also considered prime candidates for being cosmic particle accelerators. Within the turbulent jet, protons can be accelerated to extreme energies. These cosmic rays can then interact with photons or gas within the jet, producing two key byproducts: high-energy gamma rays and high-energy neutrinos. Detecting these neutrinos is incredibly difficult, but in 2017, a landmark event occurred. The IceCube Neutrino Observatory in Antarctica detected a single, very high-energy neutrino and immediately sent an alert to astronomers worldwide. Telescopes across the globe swiveled to the direction it came from and found a known blazar, TXS0506 plus 056, in the middle of a major flare. This was the first time a high-energy neutrino was confidently traced back to a specific astronomical object, providing the first direct evidence that blazar jets are indeed powerful cosmic ray accelerators. Radio observations were crucial, pinpointing the location and providing essential information about the physical conditions in the jet where these interactions were taking place. As astronomers gathered more data, they noticed a pattern, proposing a classification scheme known as the Blazar sequence. It suggested an inverse correlation between the luminosity of a blazar and the peak frequency of its emission. According to this sequence, the most luminous blazars, the FSRQs, have their synchrotron peak at lower energies, like infrared, while the least luminous ones, the VLBIs, have their peak at higher energies, like X-rays. The initial physical interpretation was that this represented a cooling effect. In powerful FSRQs, the jet is filled with photons from the bright accretion disk. These external photons cause the jet's electrons to cool rapidly and efficiently, so their emission peaks at lower frequencies. In the less powerful VLBIs, the external photon fields are weaker, so the electrons don't cool as much and can be accelerated to higher energies, shifting their peak to the X-ray band. However, the blazar sequence is intensely debated. Some argue it's not a true physical sequence, but an illusion created by selection effects, the fact that our telescopes are more likely to detect the brightest objects. Still, the sequence remains a valuable framework that helps guide our thinking. Our journey to understand the blazar's gaze is far from over. A new generation of powerful telescopes is poised to revolutionize the field. The Square Kilometre Array, or SKA, is an international project to build the world's largest radio telescope. With thousands of antennas spread across Australia and southern Africa, the SKA will offer unprecedented sensitivity. It will be able to detect tens of thousands of new blazars, including fainter and more distant ones, providing a massive statistical sample to test our models. Its incredible sensitivity will allow for more detailed movies of jet evolution and will probe the faintest magnetic field signatures. In the multi-messenger domain, the future lies in enhanced coordination with upcoming gamma-ray observatories, like the Cherenkov Telescope Array, and next-generation neutrino detectors like IceCube Gen 2. Radio astronomy, with the SKA and enhanced VLBI networks, will be more critical than ever, providing the high-resolution imaging needed to interpret multi-messenger alerts and pinpoint the exact physical processes responsible for the universe's most extreme events. Blazars represent nature's most extreme laboratories. In their relativistic jets, matter is accelerated to speeds we can only dream of achieving on Earth. They are lighthouses in the cosmic dark. They're intense, focused beams of radiation carrying information from the very edge of supermassive black holes across billions of years of cosmic history. Staring into this gaze is a task made possible by the remarkable power of radio astronomy. By linking dishes across the globe, we have built a telescope the size of our planet to resolve the unresolvable and watch as plasma flows at nearly the speed of light. As we stand on the cusp of a new era of discovery, the Blazar's gaze, once a complete mystery, is slowly being unraveled, revealing not just the secrets of black holes and galaxies, but the fundamental laws that govern our universe at its most extreme.